Okay, continuing our discussion on how to report measurements and reporting your best estimate of a measurement. There are some special cases, okay? We talked about how your uncertainty, a way to quantify your error and your uncertainty should be plus or minus the least count. There's some special cases, okay? So when we're using standard masses, for example, and standard masses would be, you know, the little 100-gram blocks and kilograms and whatever that we use in the lab, we generally consider the uncertainty to be 1% of that, okay? So, for example, if I have a 100-gram mass, the uncertainty would be plus or minus 1 gram. If I have 1 kilogram mass, it would be plus or minus 10 grams, for example. Does that make sense? So you really want to make sure that you understand the concept of percentages and how to find percentages of quantities. It's really important. Now, stopwatches. Okay, when we use stopwatches, notice that most stopwatches report to the 1 100th of a second, including the ones that we have. Okay. Now, if you take this least count as the uncertainty, it's ridiculous because you could never move your thumb that fast. Your reaction time is far greater than that. We'll find in class, okay, that our reaction time is about 0.3 seconds. Okay. Now, if we use 0.3 seconds, that's pretty reasonable, okay? So I don't ever want to see you guys reporting times you measure on stopwatches to the 100th of a second. You will always lose points for that. Now, in reality, if you're measuring something, if you have a reaction time of 0.3 seconds, you have that reaction time when you start and when you stop. So really your uncertainty should be plus or minus 0.6 because it's 2 times that. Now, we'll just simplify things. If you want to use plus or minus 0.6, I'm cool with that. I use plus or minus 0.3. You know, maybe technically 0.6 is better, but you know, it's okay with me if you use 0.6, all right? Okay, so example 4. Go ahead and pause and read this past paper, paper 1 question from a previous IB, a recent, actually, IB physics exam. Okay, so this shows you a centimeter rule, and there's a rod, and it's asking you to report the measurement, the best measurement with this uncertainty of the length of the rod. Okay, so what do you guys think? Well, the IB, doing it in the IB way, the way that I've described to you, the answer would be C. Okay, so it's 5.0 plus or minus 0.1 centimeters. Okay, so you can see that it's 5. I think you would all agree that that's 5. Right? Like exactly 5. Well, not exact, but as close as you can estimate using this rule. Okay? And your least count would be your smallest graduation. Now, you might think that you could do it beyond the least count. I don't think you could with this rule, but that's up to you. And I think if you claim that you could, I would question that. Okay? But notice how the choices you have in the problem, none of them estimate beyond the least count anyway. Okay? Okay, now, our goal, remember, is to be as certain as possible about a measured value. And the more certain our measured value, the more the lower the uncertainty, right? So certain and uncertainty are obviously related. So we take several measurements and we average them all together. However, the reported uncertainty in your average value is different than the uncertainty in your measurement. This is super important for you guys to understand the difference between the 2 different kinds of uncertainties, okay? Now, the precision of the instrument is not the same as your uncertainty in the measurement, okay? I'm going to show you guys some examples of this. Now, several measurements give a range of values. The real value hopefully is within this range, unless you're using super faulty equipment or you haven't slept for a week. The uncertainty is determined by dividing the range of values by 2. Okay, that's the max minus the min divided by 2. Okay, the stated uncertainty must match the number of decimal places. We've gone over that. Stated uncertainty should have only 1 significant figure if possible. And you know, you should really, I'm going to cross that out. And I would put 1 non-zero digit if possible, which essentially amounts to the same thing in a lot of cases. At least 3 measurements of everything is required in the IB. The more the better. And I almost always give you time to do more. So if you can do 6 or 7 or even 10, your labs will be graded. You will possibly get a higher score, if you know what I mean. Do not be afraid to throw out data that is clearly a mistake. Okay, and it's up to you to do that. You can do that, but you got to justify it. Okay. All right, let's try this one, example 5. Go ahead and read this one. Pause the video, read it, and try it. Okay, so we have 6 different students measuring the same lamp, the resistances of a lamp. In ohms, these are the answers. There's quite a range, okay? So how do we know which one's right? Well, none of them, it could be possible that not any of them are right, okay? But we got to trust our experimenters, in this case students, that they did something right, and we got to take these values and do what we can with it, okay? So it's not up to you to judge whether the values you're given are faulty or not. If they're given to you, you have to trust the experimenter. So the question is, what should the students report as the best value of the measurement of the resistance of this lamp, okay? Well, you take the average, you get 643 ohms, okay? The range divided by 2, the range is 57 ohms, divided by 2 is 29 ohms, okay? So the best reported value for the resistance of this lamp would be 643 plus or minus 30, not 29, because we want to have, if possible, one significant figure. If we can't have that, we want to have one non-zero digit. So it's 643 plus or minus 30 ohms is the way that we would do this, okay? The next example, why don't you try this one? Pause the video. Okay, pretty cool. So perpendicular measurements are made of the diameter of a cylinder, okay? Maybe 6 different students or the same student 6 different times. How do we report the value, okay? Well, first of all, you notice that one of the values is seems crazy wrong. 26.1, definitely not, I'm not grooving on that, and you shouldn't groove on that either. I don't know what happened there, but we're going to throw it out. You have to justify it in the lab report, okay? So you present your results as these results, okay? The average of the good 5 is 21.9, the range is 0.5, the range divided by 2 is 0.25, so you'd say 21.9 plus or minus 0.3, okay? So again, your decimal places have to match up in both your stated value and your uncertainties. Super important, okay? All right, now when taking time measurements with a stopwatch, the stated uncertainty can't be unreasonably small, no matter how small the range. So you would improve data accuracy by measuring the time taken for several successive events, like the oscillation of a pendulum, okay? If the event is not periodic, you would use a vernier probe if possible, okay? So let's see, example 7. For a pendulum, 20 oscillations are timed in seconds at, okay, interesting. So some student is measuring 20 oscillations of a pendulum, okay? What's the best stated value for the period of this pendulum? Interesting. Try it. Okay, so very obviously the average is 14.72, okay? The range in values is 0.06, but you can't report the value for 20 oscillations as 14.72 plus or minus 0.03 because that's too small, okay? So you must report it as 14.72 plus or minus 0.30, okay? Now, if this bothers you, this next part will not bother you, okay? Remember, you measured 20. You're trying to find t. You're trying to find 1. So you would multiply both of, you would divide both of these numbers by 20, okay? So really, t is 0.7360 plus or minus 0.0150 seconds, okay? So how cool is that, all right? Now, because you're dividing by 20, 20 is a counting number, so the 1 sig figs does not limit the sig figs in your answer. So you can keep all 4 of the sig figs in the 14.72 and report your final period as 0.7360 plus or minus with 1 non-zero digit in your uncertainty. That would be 0.0200 seconds, okay? So that's the way we do it. The manner in which you report measured and calculated values is entirely up to you as an experimenter, as long as you follow these rules, okay? You got to be realistic in your precision. You got to be able to fully justify reported measurements and calculated values, okay? All right. So we're going to talk about absolute and percent uncertainties here for just a minute before I conclude this video, okay? There are two ways to quantify errors as uncertainties: absolute uncertainties and percent uncertainties, okay? An absolute uncertainty would be plus or minus something in the units of the thing that you're measuring, okay? It's called an absolute uncertainty. So it's plus or minus delta x, where x is the thing that you're reporting a measurement for. A percentage uncertainty is the uncertainty expressed as plus or minus the percent. And what that amounts to is the change in that, the uncertainty in that, over the actual value times 100. Does that make sense? I'll do a couple of examples, okay? So for example, as an absolute uncertainty, length 234 plus or minus 2 millimeters, period 1.6 plus or minus 0.3 seconds. Those are absolute uncertainties. They have the same units as the stated measurement, and they all begin as an absolute uncertainty. All uncertainties begin as an absolute uncertainty because that's what you measure according to the precision of your instrument, okay? So percentage uncertainties are then actually calculated based off of absolute uncertainties. So examples of percentage uncertainties, the same ideas as before. For that length, that was 234 plus or minus 2 millimeters, okay? It's actually 234 plus or minus 8.5%. And this is how you write it. You put your plus or minus percentage in parentheses. So you see what I did here, okay? I divided the 2 by 234 and I multiplied that by 100 to get a percentage. In this case, I divided the 0.3 by 1.6 to get the 18.8%. Okay, does that make sense? You really want to work through that if you're not getting it right now, and make sure that you get it before you end this video and you start the next one.